All right, so we're going to do some more examples now, and we've got the alternating series test here to tell us if our alternating series is convergent, and we have our divergent test, which means the limit of a sub n does not equal 0 or does not exist, then our series is divergent. So let's look at our first one. Our b sub n here is n squared over n cubed plus 4. And if you were to graph this, right, as an f of x, it gives us this graph. So you can see it's initially increasing, but after we hit an x of 2, so after our second term, it's now going to decrease from here on out. So to show us that it's decreasing, what we can do is solve this, just like we've done before, factor out an x. And so x right here would equal 2. So at 2 is when we're going to get our maximum. And so if we test this now, after 2, we just need to make sure that it's eventually decreasing. Now if we plug in, say, 3, heck, let's plug in 100, because everything after that will either decrease or increase. So if I plug in a positive, right, I get 100, but this is 100 cubed, which means this is going to be negative. So we just showed condition 1, decreasing, check. So now all we have to do is show that the limit as n approaches infinity of our b sub n is equal to 0. So condition 2. So now if we divide everything by n cubed, we get 1 over n, 1 plus 4 over n cubed. And that goes to 0, that goes to 0, so it equals 0. Check. Therefore, the series converges by the alternating series test. So this is one way to show it. You take the derivative, and again, it just needs to be alternating. You may be thinking, well, what about this? Well, that's going to converge because it's already finite. We're just going to plug in 1 and 2 and add those up. Converged. So now we can find from 3 on, basically, is what we're looking at. So we're breaking the series up into its parts. We're looking at it as the sum from n equals 1 to 2. I'm going to put a sub n plus 2 to infinity, sorry, 3 to infinity of a sub n to get the whole thing. And so that's really the one we're looking at now, is to see if that's convergent. And it does decrease from 3 on. Oh, let's take a look at how it looks with Desmos. So if I push play, you can see how it alternates between the two, but it is eventually converging. Let's take a look at another one. All right, so again, both of these conditions have to be met. So if you look at the next one that we're doing, we take our b sub n, which equals 3n minus 1 over 2n plus 1. Then we would say that the limit as n approaches infinity of 3n minus 1 over 2n plus 1 is going to give us 3 halves, which does not equal 0. So that means the part 2 is a no. So there's no reason to even continue the test if one of the parts doesn't work. So now we're going to try and show that it is divergent. And the first thought is to use the divergent test because it does not equal 0. And so you can kind of look at it that way. But let's take a look at it and so you can see what is going on here. So we rewind this and hit play. So you can see it is literally alternating back and forth. It's not going towards the same thing like we had in the previous one. So what's really happening is as we get farther and farther out, right, we're really just alternating between that add 3 halves and add negative 3 halves, add 3 halves, add negative 3 halves, add 3 halves. And so you can actually see that if I go over here that it is a 1.5 between them. So it's literally subtract 3 halves, add 3 halves, subtract 3 halves, add 3 halves. So we say the limit as n approaches infinity of our new b sub n, using the divergence test, does not exist because it will actually alternate between 3 halves and between 3 halves and negative 3 halves back and forth. So by and we're using this one now, the divergence test, if the limit of a sub n does not equal 0 or does not exist, then the series a sub n is divergent. So by the divergence test, the series diverges. So it's a way to use both of those together. You have one that says that it can't be 0, and the other says that it equals 0, or does not exist, of course, on that one. All right, the last one is just to show you it doesn't have to be -1 all the time. You can actually use sine and cosine to generate these as long as you include the pi in there. So let's look at just the sine. So n equals 1, and we're just going to do like 5 just to get an idea of, we can put the infinity on there, it's fine. But we're going to go sine of pi n plus 1/2 so that we can change this into an alternating series. So now if I were to plug in 1, this would become sine of 3 pi over 2 plus sine of 5 pi over 2, and then so on, plus sine of 7 pi over 2 plus ... And so if you remember with sine of 3 pi over 2, that's -1 plus 1 minus 1. So it's going to be a -1 to the power of n. So this is the sum from n equals 1 to infinity, -1 to the power of n, and then we always double check it. Plugging in 1 gives us -1, it checks, and then now we have our b sub n. So our b sub n here is equal to 1 over 1 plus rad n, and so we check it with the 1 plus rad n, and I'm going to put it over here this time. I'm going to add an n plus 1 for my next term, and you can see that it is decreasing. So if I remove that minus that plus 1 right there, it would make it a bigger fraction. So this is smaller, larger, part 1, decreasing, check. And now we can go off to the end, the limit as n approaches infinity of 1 over 1 plus rad n. Divide everything by rad n. And that goes to 0, 0, and we end up with 0. So condition 2, check. Therefore, the series is convergent by the alternating series test. And we also know that b sub n here is positive because it's 1 over rad n, so we can put in there greater than 0. Let's take a look at the graph. And so I hit play, and you can see they are converging.